Welcome to the deep dive. Today, we're going to tackle something pretty amazing, actually. It starts with you, with your own brain. Think about how you can just glance at a number someone scribbled down, maybe really messy, maybe tiny, like 28 by 28 pixels, and you just know it's a three-put instantly. It doesn't even matter if the pixels are totally different from the last three you saw. Somehow your brain, your visual cortex, just figures it out effortlessly.
It really is astonishing when you stop and think about it, isn't it? Because that task, which feels so simple, so trivial for us, well, trying to get a computer to do the same thing using traditional programming, that's a whole different story. It's incredibly difficult. Imagine trying to sit down and write out step-by-step rules. If this pixel is dark and this one next to it is light, maybe it's an edge.
Yeah.
You'd get tangled up in endless if statements trying to cover every possible way someone could draw a three. The slant, the loops, how thick the line is. It's a nightmare.
Yeah, like writing a rule book for something that's just inherently fuzzy. You'd never finish. So that programming nightmare, that's exactly the kind of problem neural networks are designed to handle. And that's what we do here at the Deep Dive. We're your shortcut to understanding these complex topics. We peel back the layers, show you the mechanics, but without drowning you in jargon. Today, we're making that leap. From our own mysterious, crazy smart visual cortex to understanding how a computer can pull off similar feats, we're going deep into the brain of AI.
That's right. And maybe brain is a strong word. It's more like the fundamental building blocks. We're focusing on artificial neurons. What are they? How do they connect to form these things called neural networks? And we'll explain it all in a way that hopefully makes intuitive sense, even if you've never touched this stuff before. No tech background needed. The goal is for you to get a real gut feeling for how these systems work at their core and why they're so powerful.
Okay, great. And we're drawing on some really good explanations out there, right? Sources that break this down step by step.
Exactly. We've looked at sources that guide you from the simple idea of a neuron all the way to the clever algorithms that let these networks actually learn from data.
So what's the roadmap for you, our listener, today? What will you walk away with?
Well, you'll get the connection, the loose inspiration, really, between artificial neurons and biological ones. You'll see how information, like that image of a three, flows through the network layers. We'll talk about weights and biases, what they actually do, and then we'll demystify the big learning algorithms, gradient descent and backpropagation. These are the engines of learning. By the end, you should have a really clear sense of why these basic ideas are absolutely crucial for understanding all the modern AI buzzwords like deep learning and those transformer models everyone's talking about.
Sounds like a plan.
Yeah.
You mentioned the biological inspiration being loose. How much should we really lean on that brain analogy? Let's start right there. What is an artificial neuron?
Good question. It's definitely more of a conceptual borrowing. The real power isn't in making a perfect fake brain cell, it's in the network idea. So an artificial neuron at its heart is basically just a thing that holds a number, a very simple processing unit. This number, usually kept between 0 and 1, is called its activation.
Activation, like how active it is.
Exactly. You can think of it like a dimmer switch. If the activation is high, close to 1, the neuron is lit up, it's strongly active. If it's close to 0, it's dim or inactive. It takes in numbers from other neurons, does a quick calculation, and then spits out its own activation value. That's pretty much it.
Okay, so super simplified compared to a real neuron, but it captures that idea of processing inputs and then firing or activating.
Precisely. The magic isn't in the single neuron, it's in having potentially millions of these simple things connected together and influencing each other. Just like in the brain, one neuron firing affects the next ones down the line.
Got it. So if these neurons just hold numbers, how does something like an image get into the network to begin with? Where does the data actually enter?
That's the job of the input layer. Think of it as the network's retina, maybe? Let's go back to that 28 by 28 pixel image of a handwritten digit. 28 times 28 is 784. So for the input layer, we'd have 784 neurons. Each one corresponds to a single pixel in the image.
Okay, so each neuron represents one dot in the picture.
Exactly. And the activation of each of those 784 input neurons is just set to the grayscale value of its corresponding pixel. So if a pixel is pure black, its neuron's activation might be 0. If it's pure white, maybe 1. And all the shades of gray are numbers in between 0 and 1. That whole grid of pixel brightness values becomes the initial pattern of activation in the input layer. That's how the network sees the image.
That makes perfect sense. Pixels in, numbers out. Well, numbers in the first layer. So what about the other end? How does it give us the answer the output.
Right, the output layer. For our digit problem recognizing digits 0 through 9, the output layer would typically have 10 neurons. Each of these 10 neurons stands for one specific digit. One for 0, one for 1, one for 2, and so on up to 9.
So 10 possible answers.
10 possible answers. And after the network has done all its processing, chewed on the input image through its internal layers. The neuron in this output layer that has the highest activation, the one that's lit up the brightest, closest to 1, that's the network's decision. If the neuron representing 3 is the brightest, the network says, I think this is a 3. If the 7 neuron is brightest, it votes for 7.
Input layer takes the picture, output layer gives the verdict. But the real mystery, the giant question mark you mentioned, is what happens in between, right? These hidden layers.
Exactly. The layers sandwiched between the input and the output are called hidden layers. Hidden because, well, their job isn't immediately obvious. They don't directly represent pixels or the final answer. In the classic example network people often start with, the choice was kind of arbitrary. 2 hidden layers, and each of those layers has 16 neurons. And yeah, initially you look at them and think, what on earth are these 16 neurons doing? How does that help recognize a digit? It's not clear at first glance.
So what's the thinking? Why have them at all? What's the hope for what they accomplish?
The hope, the motivation, really is about hierarchy. It's the idea that the network can learn to break down the big, complex problem, recognizing a whole digit, into smaller, manageable subproblems. Think about how we might recognize a digit. Like, a 9 has a loop on top and a straight line down, right? An 8 is like 2 loops. So the hope is that maybe the neurons in the first hidden layer, the one right after the input, learn to detect really simple things. Little edges, maybe horizontal lines here, vertical lines there.
Okay. Like basic shape components.
Exactly. Little primitive features. Then maybe the neurons in the next hidden layer, the second one, learn to combine those simple edges. They might learn to recognize slightly more complex patterns like, oh, here's a loop forming, or here's a line crossing another line. And then finally, the output layer takes those combined patterns, loops, lines, intersections, and puts them together to say, that combination looks like a 9.
That makes a lot of intuitive sense. It's like building up complexity layer by layer, from simple lines to complex shapes.
Precisely. And this idea of layered abstraction, building up representations, it's super powerful and applies way beyond images. Think about understanding speech. The input is raw sound waves. The first layer might detect basic frequencies or phonemes. The next layer combines those into syllables. The next layer combines syllables into words, then words into phrases, you see. Each layer handles a more abstract level of the problem. The amazing part is the network often figures out these useful intermediate steps on its own during training.
Okay, so the activations ripple through. Input layer lights up based on the image that causes a pattern in the first hidden layer, which causes a pattern in the second, and finally the output layer lights up with the answer. It's like dominoes falling.
That's a great way to picture it, a cascade of activations. The pattern in one layer directly determines the pattern in the next. Feed forward, we call it. An input image triggers the first set of dominoes, and the way they fall dictates how the next row falls, and so on, until the last row tells you the result.
All right, structure makes sense. Input, hidden layers, building complexity, output gives the answer. But we skipped a crucial step. How does the pattern in one layer actually determine the pattern in the next? How does a neuron know how much attention to pay to the neurons before it? That's where the real tuning happens, isn't it? The knobs and dials.
You nailed it. That's exactly where the network's learning parameters come in. The weights and biases. Let's start with weights. Imagine every connection between a neuron in one layer and a neuron in the next layer. Each of those connections has a number assigned to it, called a weight. This weight represents the strength, or maybe the importance, of that specific connection.
So like how much influence one neuron has on the next one.
Exactly. If you have a neuron in the second layer, it's connected to all 784 neurons in the input layer, right? Each of those 784 connections gets its own weight. Some might be strong positive weights, some strong negative, some close to 0.
Okay, so give me an example. If a neuron in that first hidden layer was trying to detect, say, a vertical edge in the middle of the image, how would the weights help?
Great example. So that neuron wants to light up when there's a vertical edge there. What you'd want is for the weights connecting to the pixels in that middle vertical region to be positive, maybe strongly positive. And you'd want the weights connecting to the pixels immediately to the left and right of that region to be negative.
So it wants the middle pixels to be bright and the surrounding ones to be dark.
Precisely. Then when you calculate a weighted sum, multiplying each input neuron's activation by its connection weight and adding them all up, that sum will be highest when you have exactly that pattern. Bright pixels down the middle, dark ones on the sides. You can almost visualize the weights themselves as a little grid, a filter. Green for positive, red for negative. It shows the pattern the neuron is looking for.
Okay, that makes sense. The weights create a pattern filter. So you calculate this weighted sum. What happens then? You mentioned biases too.
Right, so you've got this weighted sum. It could be a big positive number, a big negative number, or somewhere in between. Before we decide the neuron's final activation, we add one more number to it, the bias.
Another parameter. What does the bias do differently from the weights?
It's another crucial parameter, yeah. Think of the bias as setting the neuron's baseline tendency to activate. It's like an internal threshold. It basically decides how high that weighted sum needs to be before the neuron starts to get meaningfully active, before it really lights up. For instance, if a neuron has a very large negative bias, say -10, the weighted sum of its inputs needs to be greater than +10 just to overcome that negative bias and start activating. It makes a neuron harder to turn on.
So it needs a really strong pattern match from the weights to fire.
Exactly. Conversely, if the bias is positive, the neuron might activate even with a relatively weak input pattern. It's more easily excitable. So the bias gives each neuron its own independent level of reluctance or eagerness to fire, separate from how strong its input connections are.
Weights filter for patterns, bias adjusts the activation threshold. Got it. But then, squishification. The term
Right.
stuck with me. What's that about? Why squish the number?
Huh? Yeah, it's a memorable term. So after you add the bias to the weighted sum, you get a raw number. Could be 50, could be negative 20, could be anything. But we usually want our neuron activations to be nicely contained, typically between 0 and 1. So we pass this raw sum through an activation function that squishes the value into that range. This squishification step is super important. It introduces nonlinearity. Without it, the whole network, no matter how many layers, would just collapse into one big linear function, like fancy multiplication. But adding this nonlinear squish at each layer allows the network to learn much, much more complex relationships in the data. It's essential for recognizing wiggly digits or understanding messy human language. Simple lines just won't cut it.
Okay, nonlinearity is key. Are there different ways to squish? You mentioned sigmoid and ReLU before.
Yeah, there are several popular ones. Historically, the sigmoid function was very common. It looks like a smooth S-curve. It takes any input number. Very negative numbers get squished close to 0. Very positive numbers get squished close to 1. And numbers around 0 fall smoothly in between. It was partly inspired by that biological idea of a neuron being either off 0 or on 1, but with a smooth transition.
But you said modern networks don't use it as much.
That's right. Especially in the hidden layers, sigmoid isn't used that often anymore. The go-to function nowadays is usually ReLU, which stands for rectified linear unit. ReLU is much simpler, actually. It just says, take the maximum of 0 and the raw sum, weighted sum plus bias.
So if the sum is negative, output 0. If it's positive, just output the sum itself.
Exactly. If the sum is below 0, the neuron is off, activation 0. If the sum is positive, the activation is just that positive value. It turns out the simplicity makes networks much easier and faster to train. It avoids certain problems, like vanishing gradients in deep networks that sigmoid could sometimes cause. It just lets the learning signal flow back more easily during training.
Okay, simpler is often better, I guess. So pulling it all together, each neuron takes weighted inputs, adds a bias, applies ReLU or something similar. The whole network is just layers of these things.
Pretty much. Each neuron is like a mini function, and the whole network, you can think of it as one enormous, absurdly complicated function. It takes in 784 numbers, the pixels, and spits out 10 numbers, the digit probabilities. And the sheer number of parameters inside is mind-boggling. That simple example network we talked about, 784 inputs, 2 hidden layers of 16 neurons, 10 outputs, it has almost exactly 13,000 weights and biases in total.
Whoa. 13,000. Seriously, that's 13,000 adjustable knobs and dials.
13,000 little parameters that define the function. It's a staggering number when you think about tuning them all, but that's the point. Having that many parameters gives the network incredible flexibility to model complex patterns. And learning, in this context, just means finding the right settings for all 13,000 of those numbers so that the network consistently gets the right answer for the digits. It's an optimization problem on a massive scale.
I can only imagine trying to write the code for that, tracking every single connection.
Well, thankfully, we don't have to. That's where linear algebra saves the day. We use vectors to represent the activations in a layer and matrices to represent all the weights connecting two layers. The whole complicated process of calculating weighted sums for an entire layer boils down to a single, clean matrix vector multiplication. This isn't just neat mathematically. It makes the code way simpler and, crucially, much, much faster to run, especially on hardware like GPUs that are optimized for these kinds of matrix operations. So it's complex in behavior, but elegant in its mathematical structure.
Okay, so we have this incredibly complex 13,000 parameter function neatly packaged with matrices. When you first set it up, you just initialize all those weights and biases randomly, right? So the network starts out just guessing randomly. Pretty horribly, I imagine.
Oh, absolutely. When you initialize randomly, the output is complete garbage. It's just noise. The network is doing something, but it has no idea what it should be doing. It's definitely a bad computer at that point.
So how does it learn it's being bad? How does it get feedback that it needs to improve?
That's the critical role of the cost function, sometimes called a loss function. The cost function is a way to measure exactly how bad the network is performing. It quantifies the difference between the network's actual output and the output we want it to produce. It's the signal telling the network, you messed up, and here's how much.
Okay, make that concrete for me. Back to the image of a 3. How do we calculate the cost for just that one image?
Sure, so input image of a 3-punt. The desired output is activation 1 for the 3-punt neuron and 0 for all the other 9 neurons. 0, 1, 2, 4, 5, 6, 7, 8, 9. Now let's say the network actually outputs some random activations, maybe 0.2 for the 3-foot neuron, 0.6 for the 8-foot neuron, and small numbers for the others. To get the cost for this single example, we look at the difference between the actual output and the desired output for each of the 10 neurons. We square each of those differences, and then we add them all up.
Squaring them makes bigger errors count a lot more, right?
Exactly. If the network is way off, like outputting 0.9 for 8 when it should be 0, that squared difference is large. If it's close, like 0.9 for 3 when it should be 1, the squared difference is small. So a high cost means the network is making big mistakes on this example. A low cost means it's doing well.
And that's just for one image. How do you measure performance across the whole training set, thousands of images?
Simple enough, conceptually. You calculate the cost for each individual training example, and then you just average those costs together. This average cost over the entire dataset gives you a single number that represents the overall lousiness or badness of the network in its current state. And here's the mind-bending part. This total cost function is itself this incredibly complicated function. Its inputs are all 13,000 weights and biases. Its output is that single badness number. The entire goal of training is to tweak those 13,000 parameters to find the combination that makes this cost number as low as absolutely possible. Minimize the cost.
Okay, minimizing the cost means better performance. But finding the minimum point in a 13,000 dimensional landscape, that sounds completely impossible. How do you even start navigating that?
Yeah, you can't just solve it on paper like a simple algebra problem. That's where the workhorse algorithm comes in, gradient descent. It's an iterative process, a way to navigate that landscape step by step.
Iterative. So not finding the answer all at once, but taking steps towards it.
Exactly. Think of the analogy. You're on a foggy mountain range, completely blindfolded. You want to get to the lowest valley. What do? You can't see the whole map. So you feel the ground right where you are. You figure out which direction is steepest downhill from your current spot. And then you take a small step in that direction. Then you repeat. Feel the slope, take a step downhill. Feel the slope, take a step downhill. By constantly moving in the locally steepest downward direction, you'll eventually end up in some kind of valley, some low point.
Like a ball rolling down the hill, it just naturally finds its way downwards.
That's the intuition. Now, in our high-dimensional space with 13,000 parameters, we use a mathematical concept called the gradient. The gradient is a vector, basically an arrow that points in the direction of the steepest uphill climb on the cost landscape from your current position. So naturally, if we want to go downhill, we just take the negative of the gradient. That points in the direction of steepest descent.
So the negative gradient always shows the quickest way to reduce the cost. Right here, right now.
Exactly. It's the most efficient direction to step in to lower your cost based on your current location. And there's more. The length of that gradient vector tells you how steep the slope actually is. A long gradient means you're on a steep cliff, and a step will lower the cost a lot. A short gradient means you're on flatter ground, maybe near a minimum.
And you mentioned bang for your buck relating to the gradient. How does that work with the 13,000 parameters?
Right. That negative gradient vector has 13,000 components, one for each weight and bias. Each component tells you two things about its corresponding parameter. First, the sign, plus or fleck, tells you whether to nudge that specific weight or bias up or down to decrease the cost. Second, the magnitude of that component tells you how sensitive the cost is to that particular parameter. A large magnitude means changing that weight bias will have a big impact on the cost high bang for your buck. A small magnitude means tweaking it won't change the cost much. So the gradient automatically tells us not just which way to nudge everything, but also which nudges are the most important ones to make.
That's incredibly useful. Focus the effort where it counts the most.
Definitely. Now, this whole process relies on the cost function being reasonably nice and smooth. You need to be able to calculate a slope everywhere. If it had sharp jumps or breaks, the idea of a gradient wouldn't make sense. That's one reason why activation functions like sigmoid and ReLU are smooth or piecewise smooth. They allow gradient descent to work. Having just binary O1 activations would make this much harder.
Makes sense. But what about getting stuck? That ball rolling downhill could just roll into a little ditch, not the absolute lowest point on the whole mountain range. Does that happen here?
Oh, absolutely. That's a classic issue. Gradient descent guarantees finding a local minimum, a point where you can't go any lower by taking a small step in any direction. It's a valley. But there's no guarantee it's the global minimum, the absolute lowest point in the entire 13,000 dimensional landscape. The network might find a pretty good solution, but maybe not the mathematically perfect one. Fortunately, in these very high-dimensional problems, it often turns out that many local minima are actually quite good, and finding the absolute best one might not even be necessary for good performance.
Okay, so gradient descent gives us the direction and the relative importance for changing all 13,000 parameters. But calculating that gradient, figuring out how sensitive the final cost is to every single one of those knobs, that sounds like the really heavy lifting computationally. How's that done efficiently?
You've hit on the engine room again. That's where backpropagation comes in. It's the algorithm that efficiently computes that massive, complex gradient. Backpropagation is the workhorse that calculates exactly how much each of those 13,000 weights and biases contributes to the final error, allowing gradient descent to know how to adjust them. Without it, training deep networks would just take way too long.
Okay. Can we get the intuition for backpropagation? How does it work without getting totally lost in calculus?
Let's try. Think about propagating the error, or the desired changes, backwards through the network. Imagine, again, we feed in an image of a two-moon. The network is untrained, output is random. Say the 7-fit neuron is way too high and the 2 neuron is way too low. We know what we want the output layer to look like. High activation for 2 months, low for others. We can't directly change those activations, remember, they're results. But we can figure out, for each output neuron, how much we wish its activation would change. Increase the 2 money, decrease the 7, decrease the 8, etc., proportional to how far off they are. These are like initial error signals.
Okay, so we know the desired change at the very end. How does that tell us what to do earlier in the network?
Right. Let's focus on that 2 neuron we want to boost. What influences its activation? 3 things, mainly. Its bias, the weights of connections coming into it, and the activations of the neurons in the previous layer, the last hidden layer. Backpropagation figures out the impact of each. To increase the 2 neurons' output, we could increase its bias, or we could increase the weights on its incoming connections. Now, which weights should we increase the most? The ones coming from neurons in the previous layer that are currently brightest, highest activation. Why? Because those weights get multiplied by large activation values, so increasing those weights gives you the most bang for your buck in boosting the 2 neurons' weighted sum, and thus its final activation.
So you prioritize strengthening connections from already active neurons in the previous layer. That sounds kind of like that neuroscience idea, neurons that fire together, wire together.
It's a really interesting, though loose, parallel. Hebbian learning talks about strengthening connections between neurons that are simultaneously active. Backpropagation effectively does something similar. The biggest increases in weights, stronger wiring, happen between neurons that are active and the neurons that we want to become more active. It's a neat resonance.
Okay, so we adjust the weights and bias for that 2 neuron, but didn't you say it also sends a signal back to the previous layer, like what it wishes had happened there?
Exactly. The 2 neuron figures out how it wishes the activations in the second to last layer had been different to help it reach its target value. For instance, if a connection from a previous neuron has a positive weight, the 2 neuron wishes the previous neuron had been more active. If the weight was negative, it wishes it had been less active. But here's the key propagation part. The 2 neuron isn't the only one with wishes for that previous layer. The 0 neuron, the 1, the 7, all the output neurons have their own desired adjustments for that same second-to-last layer based on their own errors and connection weights. Backpropagation cleverly combines all these wish lists. It adds up the desired changes from all output neurons for each neuron in the second-to-last layer. This combined nudge list tells us how that second-to-last layer as a whole should have behaved differently. And then we just apply the same logic recursively, one layer back at a time. We use the desired changes for the second to last layer to figure out the desired changes for the weights connecting to it, and the desired changes for the layer before that, all the way back to the first hidden layer.
Wow. Okay, so the error signal starts at the output where we know the right answer, and it flows backwards, layer by layer, distributing the blame or the needed adjustments proportionally to all the weights and biases that contributed to the error. That's actually really elegant.
It is. It's a mathematically beautiful way to figure out the gradient. But remember, everything we just described, calculating those desired nudges for all 13,000 parameters, that was based on just one training example, that image of a 2. If we only adjusted the network based on that one image, it would get really good at recognizing 2s and probably start classifying everything as a 2. That's overfitting.
Right, good for 2s, terrible for everything else. So you can't just listen to one example.
Exactly. To get a balanced adjustment, you need to consider all the training examples. Ideally, you'd run this backpropagation process for every single image in your data set, say 50,000 images. You'd calculate the desired weight bias changes suggested by the 3 images, the 7 images, the 9 images, all of them. Then you'd average all those suggested changes together, that final average set of nudges. That's the true negative gradient of the cost function over the entire data set. That's the direction gradient descent tells us to step in.
Okay, but averaging over 50,000 images for every single step of gradient descent, that sounds incredibly slow, like computationally cripplingly slow.
You're absolutely right. It would be prohibitively slow, especially for the massive data sets and networks used today. And that's why, in practice, we use a variation called stochastic gradient descent, or SGD. The idea is simple. Don't use the entire data set for each gradient calculation. Instead, shuffle the data randomly, then chop it up into small, manageable chunks called mini batches, maybe 100 images per batch. Then you calculate the gradient and take a step based on just the average error within that one mini batch.
So you're estimating the true gradient using just a small soffle.
Yeah.
It's not the perfect downhill direction, but it's faster.
Exactly. Each mini batch gives you a noisy but unbiased approximation of the true gradient. It's like taking lots of small, slightly wobbly steps downhill instead of one big, carefully calculated step. The common analogy is it's like a drunk person stumbling down a hill.
Yeah.
They're not taking the most efficient path, they zigzag a bit, but they're taking steps quickly and generally heading downwards. By iterating through all the mini batches, making these rapid approximate adjustments, the network zigzags its way towards a local minimum of the cost function much, much faster than calculating the full gradient every time. It works surprisingly well in practice.
Gotcha. Faster, noisier stacks. And just quickly for the mathematically inclined listener, backpropagation involves calculus, right? Something called the chain rule.
It absolutely does. At its core, backpropagation is an efficient application of the chain rule from calculus. The chain rule is what lets you calculate how a change in one variable affects another variable indirectly through a chain of intermediate steps. In our case, how does tweaking a weight in an early layer affect the final cost? Well, the weight affects the weighted sum, Z, which affects the neuron's activation, A, which affects the next layer's weighted sums, and so on, until it finally affects the cost. The chain rule provides the precise mathematical way to track the sensitivity, the derivative of the cost with respect to that initial weight, by multiplying the sensitivities of each link in that chain. It gets complex with all the connections, but that's the fundamental mechanism.
Okay, calculus aside, the intuition is propagating error sensitivities backwards. So after all this, the network structure, the cost function, gradient descent, using backpropagation with mini batches, how well does our simple, plain vanilla network actually do on recognizing those digits? Does it beat the programming nightmare?
Oh, it performs remarkably well for such a foundational approach. That network with 2 hidden layers of 16 neurons, it can typically achieve around 96% accuracy on images it's never seen before. With a few common tweaks, maybe slightly different architectures or training techniques, you can often push that up to 98% or even a bit higher. Considering it learned entirely from pixel data with no built-in knowledge of what digits look like, that's pretty impressive. It definitely beats trying to hand code rules.
96–98% is genuinely good, especially given the complexity. But you also hinted that these simple networks have some weird quirks or limitations. Like, did that hope about hidden layers learning nice, clean edges and loops actually pan out?
Ugh, that's where it gets interesting and maybe a little disappointing for our human intuition. When you actually visualize the weights learned by these simple networks, especially in the first hidden layer, they often don't look like clean, isolated edges or perfect loops. They frequently look kind of messy, almost random patterns. The network finds a solution, a combination of weights and a local minimum, that works well for classification, but it doesn't necessarily find the solution in the neat, human interpretable way we might have hoped. It finds its own way, using abstract patterns that are effective even if they don't make immediate visual sense to us.
Huh. So it works, but maybe not for the reasons we initially guessed. What about that other point memorization versus understanding? Can the network just memorize all the training images?
That's a really deep and important question in AI. There was a famous study that showed something quite startling. They took a standard image dataset but deliberately randomized all the labels. So a picture of a cat might be labeled dog, a car might be labeled tree, complete nonsense. They found that large, deep neural networks could still achieve near-perfect training accuracy on this randomized data, meaning they could perfectly memorize the entire dataset, including the wrong labels.
Whoa. So it wasn't learning concepts at all, just building a giant lookup table for the specific images it saw during training. That seems less intelligent.
It definitely raises profound questions about what learning means. If a network can perfectly fit random noise, does minimizing the cost function always equate to finding meaningful structure? However, subsequent research added crucial nuance. While networks can memorize, it turns out that training them on structured, correctly labeled data is significantly easier and faster. The optimization process converges much more readily when there are real patterns to latch onto. It suggests that the path to finding meaningful patterns in the cost landscape is somehow smoother or wider than the path to just memorizing noise. So yes, they have the capacity to memorize, but they seem intrinsically biased towards finding real structure when it exists simply because it's an easier optimization problem to solve.
That's somewhat reassuring. And what about weird inputs? If you show it random static instead of a digit, does it say, I have no idea?
Oh, typically, no, not this simple kind of network. It's more likely to just confidently give you some nonsense answer. It might look at pure random noise and declare with high confidence that it's a 4 or a 9. Why? Because the cost function we used only incentivized it to be correct on digits. It didn't penalize it for being confident out garbage. Its training was very narrow, just centered digits. Never learned a concept of not a digit or uncertainty. Making networks more robust to out-of-distribution inputs and better calibrated in their confidence is a big area of ongoing research.
So powerful but brittle in some ways. And you mentioned this basic network is old technology from the 80s or 90s. Given that, why spend so much time understanding it today?
Because understanding this foundational model is absolutely essential. It's the necessary prerequisite, the conceptual bedrock for understanding virtually all modern, more powerful neural networks.
Like learning scales before playing a concerto.
Exactly like that. The fundamental idea is neurons as processing units, layers building representations, weights and biases as parameters, cost functions quantifying error, gradient descent as the optimization engine, and backpropagation as the way to calculate the gradients. These concepts are universal in the field. Whether you're looking at deep learning, which often just means networks with many, many hidden layers, or convolutional networks for images, or recurrent networks for sequences, or the transformer architectures powering today's large language models, they all build upon these core principles. Understanding this plain vanilla network lets you grasp the fundamental logic, the underlying piece of math that makes all that advanced AI possible. It takes you beyond the buzzwords.
Fantastic. Well, that wraps up our deep dive for today. We started with something intuitive, your brain recognizing a 3N problems, and journeyed into the mechanics of how an artificial system learns to do something similar. We've seen the artificial neuron, the power of layered structures, the crucial roles of weights and biases as the network's adjustable filters and thresholds. And we demystified the learning process itself, defining badness with a cost function, finding the way downhill with gradient descent, and efficiently calculating that path with backpropagation.
Yeah, hopefully you now have a much clearer picture of how a machine can go from raw pixels to classifying digits, even if its internal strategies aren't always human-like, and acknowledging some of its surprising limitations.
And remembering why this matters. Understanding these fundamentals isn't just history. It's the key to unlocking a real appreciation for today's AI, from image recognition to language generation. It moves AI from being a black box to something built on elegant, understandable mathematical and computational ideas.
And maybe here's a final thought for you to chew on, for your own depth dive later. We've seen how machines learn to recognize patterns, often by finding efficient ways to minimize error. But that distinction we touched on between pattern matching, memorization, and genuine understanding, that remains one of the most fascinating and actively debated frontiers in AI research.
Absolutely. How do we build systems that don't just perform tasks, but generalize robustly, understand context, and maybe even grasp meaning in a deeper way? Engineers are constantly refining these foundational ideas, building architectures like transformers on top of these principles, pushing towards more capable and perhaps more understandable AI.
We really hope this exploration gives you that solid foundation to follow those developments, maybe dig into some code examples, or explore the math further if you're inclined. You've got the core concepts now.
Thanks for joining us on the deep dive. We'll catch you next time.